Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Carolina Bays liquefaction. This video examines the soil conditions that made possible the formation of the Carolina Bays. Soil liquefaction is an important part of the story because the most likely mechanism for the creation of elliptical features on the surface of the Earth requires the formation of inclined penetration funnels produced by oblique impacts on a plastic surface. This is followed by viscous relaxation that reduces the depth of the cavities. In geology, soil liquefaction is the process by which water-saturated unconsolidated sediments are transformed into a substance that acts like a liquid, often in an earthquake. Soil liquefaction was blamed for the building collapses in the city of Palu, Indonesia, in October 2018. On September 28, 2018, a large earthquake of magnitude 7.5 struck Indonesia. The epicenter was located 70 kilometers from the provincial capital Palu and was felt as far away as Malaysia. This event was preceded by a sequence of tremors, the largest of which had a magnitude of 6.1. Balaroa, a district in Palu, was completely obliterated by the soil liquefaction that followed immediately after the earthquake. In general, seismic vibrations of magnitude 6.0 or higher can cause liquefaction of saturated, unconsolidated soil. The idea that the Carolina Bays were created by impacts goes back to 1933 when professors Frank Melton and William Shriver from the University of Oklahoma published a research paper in the Journal of Geology. The abstract of their paper says that the smooth elliptical shape of the Carolina Bays is one of the facts that leads to the conclusion that the bays were not formed by ordinary geologic processes, and that impacts by a cluster of meteorites provide the most reasonable explanation for the origin of the bays. Melton and Shriver make a case for their hypothesis of collisions by a shower of meteors by pointing out that meteors striking plastic material at angles between 35 and 55 degrees from the vertical would produce indentations elliptical in outline. Melton and Shriver mentioned that meteors striking plastic material obliquely would produce elliptical indentations, but they did not explain how the terrain of the Atlantic coastal plain could become a plastic material suitable for creating the elliptical features, and they did not mention soil liquefaction at all. Also, Melton and Shriver implicitly associate oblique impact cavities to ellipses, which are mathematical conic sections, but they do not elaborate on how they verify that the Carolina Bays are in fact ellipses. However, throughout their paper, Melton and Shriver measure the ellipticity of the bays, which constrains their aspect ratios and makes it evident that the Carolina Bays were not formed by ordinary geologic processes. Melton and Shriver proposed that impacts at oblique angles of 35 to 55 degrees could have produced the Carolina Bays. But how did they get these numbers? Melton and Shriver noted that ellipticity varies with size. In general, ellipticity is greater for the large bays than for the small ones. The small bays are more circular. Melton and Shriver probably used the ellipticities in Figure 3 of their paper to derive the range of oblique impact angles of 35 to 55 degrees. The graph of the ellipticities provides the range of the elliptical features, and the width-to-length ratio of a Carolina Bay corresponds to the trigonometric sine of the angle of impact. This is a LiDAR image of some Carolina Bays in North Carolina. Here we can see the difference in ellipticity between the large bay on the left and the small bay on the right. Melton and Shriver attributed the smaller ellipticity of small bays to atmospheric friction as the meteors traveled through the Earth's atmosphere. The smaller projectiles would be slowed down more by their passage through the atmosphere than the larger projectiles, and the smaller projectiles would strike the Earth at a more vertical angle. In 2001, Zanner and Kuzila reported at the Geological Society of America annual meeting that Nebraska had geological structures that were comparable to the Carolina Bays, but the Nebraska rainwater basins were oriented in a northeast to southwest direction, almost perpendicular to the orientation of the Carolina Bays. The different orientation of the Nebraska rainwater basins meant that the elliptical structures in Nebraska and in the East Coast could not have been created by meteorite impacts coming from a single direction. The convergence point of their major axis is around the Great Lakes. The Nebraska rainwater basins have the same elliptical geomorphology as the Carolina Bays. Both of these geological structures can be fitted with ellipses that have the same width-to-length ratios as the bays. The fact that the bays and the basins are conic sections is a strong indication that they originated as inclined conical cavities. In 2010, Davies and Gilbride calculated the convergence point of the Carolina Bays and the Nebraska rainwater basins at Saginaw Bay based on their axial orientations. The calculation required using great circle trajectories and taking into consideration the Coriolis effect caused by the rotation of the Earth. The glacier ice impact hypothesis, published in the journal Geomorphology in 2017, describes 4 mechanisms by which the Carolina Bays and the Nebraska rainwater basins may have formed. First, a meteorite impact on the Laurentide ice sheet ejected ice boulders in ballistic trajectories. The secondary impacts by the ice boulders liquefied on consolidated ground close to the water table. Oblique impacts of ice boulders on liquefied ground created inclined conical cavities, and viscous relaxation reduced the depth of the conical cavities to produce shallow elliptical bays. Pictures of the experimental impacts contributed to the acceptance of the hypothesis for publication in the peer-reviewed journal. The determination of the convergence point at Saginaw Bay made it possible to use Google Earth to measure the distance from the source to any individual bay, and this allowed the use of ballistic equations to calculate the launch speed, the time of flight, and the maximum height of the ejected ice boulders. The launch angle can be estimated from the width-to-length ratio of the bay. The angle of impact and the distance are used to calculate the launch speed. In general, the launch speeds of the glacier ice boulders that made the bays varied from about 3 to 4 kilometers per second, depending on the launch angle and the distance to the target. The time of flight and the maximum height of the trajectory can be calculated once the launch speed is known. Notice that the different trajectories give flight times ranging from 6 to 9 minutes. This means that the ballistic sedimentation that created the Carolina Bays and the Nebraska rainwater basins took place during 3 minutes of intense glacier ice bombardment. The first impacts liquefied the soil, and subsequent impacts made inclined conical cavities. The seismic vibrations produced by the impacts speeded up viscous relaxation and reduced the depth of the inclined conical cavities to produce shallow elliptical bays. The heights of the ballistic trajectories make clear that all the ejected ice boulders were launched in suborbital space flights above the Earth's atmosphere, which only extends to 100 kilometers above the surface. Traveling in the vacuum of space, the ejected ice boulders were not affected by atmospheric friction until their re-entry. The ballistic equations make it possible to determine the time of emplacement of the bays. This image shows 2 adjacent Carolina bays with different width-to-length ratios. The bay labeled A was created by an impact inclined at 33.1 degrees, corresponding to a flight time of 386 seconds. The bay labeled B was created 15 seconds later by an impact at 35.2 degrees and a flight time of 401 seconds. As mentioned before, the different times of flight indicate that the saturation bombardment by the ice boulders lasted from about 6 to 9 minutes after the extraterrestrial impact on the Laurentide ice sheet. We come back to the subject of liquefaction, which is the topic of this video, in a very roundabout way. We need to determine the energy of the ice boulder impacts that created the Carolina Bays. We can use the size of the bay, the launch speed, the impact angle, and the type of projectile and target to calculate the energy of the impact and the size of the projectile using power law scaling equations published by Professor J. Melosh and Ross Baer. A Carolina Bay with a diameter of 1 kilometer requires an impact by an ice projectile with energy of 3 megatons of TNT, equivalent to a 7.54 magnitude earthquake. A bay with a diameter of 200 meters requires 13 kilotons of energy, equivalent to a 6.0 magnitude earthquake. From these calculations, we can see that even the impacts that made small Carolina bays had enough energy to liquefy saturated and consolidated ground. The Carolina Bays are located on the Atlantic coastal plain where the terrain is sandy and the depth to water is less than 5 feet. Similar sandy soil close to the water table is found in the terrain where the Nebraska rainwater basins are located south of the Platte River. These geological conditions virtually guarantee that the secondary impacts of the ejected ice boulders with energy of 13 kilotons to more than 3 megatons liquefied the landscape, making it suitable for the formation of inclined conical cavities. The ballistic sedimentation by the ejecta curtain lasted 3 minutes and had the energy to liquefy the ground and create penetration funnels on the liquefied ground. Viscous relaxation was the final stage of Carolina Bay formation. After the ice bombardment created penetration funnels, viscous relaxation, driven by gravity and intensified by the seismic vibrations produced by the ballistic sedimentation, decreased the depth of the cavities to create the elliptical bays in Nebraska and in the East Coast. From our contemporary perspective, we can see that Milton and Shriver had the right idea in 1933 by proposing that impacts on plastic material could have created the Carolina bays. However, we now know that the plastic material consisted of unconsolidated ground that was liquefied by the impacts themselves. We also know that the Carolina bays were not made by meteors. The discovery of the Nebraska rainwater basins and the convergence of the major axes of the bays and basins by the Great Lakes makes it more likely that secondary impacts by glacier ice boulders ejected by an extraterrestrial impact on the Laurentide ice sheet were the most likely projectiles that made the Carolina bays. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.